Hello and welcome to this video on Advanced Molecular Spectroscopy, Unit 5 on Combined Spectroscopy Problems. Well, here I have a problem for you from CSIR NET June 2018 exam, and this question was asked for 4 marks. And you usually get questions like these for 4 marks in most of your CSIR and GATE exams, right? So if you would like to have a go at this question yourself before listening to my answer to this problem, please pause the video now and have a go at it. Right. Let me continue with the question. A compound shows the following spectral data. Well, the proton NMR data is given 7.9 ppm, and it's a doublet, so that's what the D indicates, with a J value of 8 Hertz, and that corresponds to 2 hydrogens. 6.6, well, delta J is equal to 8 Hertz, and that also corresponds to 2 hydrogens. And then 4.3 ppm, it's a quartet, and with a J value of 6 Hertz, and that corresponds to 2 hydrogens. And then you have a broad singlet at 4 that corresponds to 2 hydrogens, and interestingly those 2 hydrogens are D2O exchangeable. And then there is a triplet at 1.4 ppm with a J value of 6 Hertz, and that corresponds to 3 hydrogens, right? The mass spectral data are also given at 165 M by Z, 137, 120 and 92. So presumably from the data it looks like the 165 should correspond to the molecular weight of the compound. Right. So let's look at the choices given in the exam. So you can see the 4 choices given for the exam, and interestingly they all seem to be isomers at first look. Okay, so the best way to approach this sort of a problem is to focus on the NMR data. I mean, let's forget about the mass data for some time now at least. Let's look at the NMR data. Now, if you look at the NMR data, the first important thing which comes to mind is the number of signals given, right? So you have 1, 2, 3, 4 and 5. So you have 5 different signals for your compound. So, and obviously the 7.9 there and the 6.6 there, they should correspond to the aromatic region. I think we are all familiar with that. But overall there are 5 signals in the compound, right? So let's now look at the choices, and let's start counting the number of signals, which is something which I have taught you in the initial classes of our NMR course, right? So let's start counting the number of signals in each case. So obviously for compound 1, this is going to be the first type of proton, and then you are going to have the second type of proton there, okay, and then you are going to have 3 there, 3 there, the third type of protons, 4 there, 4 there, and obviously 5. So overall there are going to be 5 protons for this particular compound. Let's now look at, so that matches our sort of the NMR data which is given there. There are 5 signals given in the data, so that matches pretty well. Let's look at compound 2, and let's do the same thing. So 1 there, 2 there, okay, 3, 4, 5, 6 and 7. So I think although there might be some overlap of the aromatic region, but still on counting the number of signals here, we get 7 signals over there, right? Now let's do the same procedure for this. Okay, so this is 1, okay, and this is 2, this is 3, this is 4, and this is 5. So the choice 3 also corresponds to 5 signals. So we have a complication here. There are at least 2 choices now with 5 NMR signals. Let's look at choice 4 and try to rule it out or see what happens here. So 1, 2, 3, 4, 5, 6 and 7, right? So again here also you have around 7 signals for this particular compound. So that technically rules out choice 2 and choice 4. So you are left with choice 1 and choice 3. out of which one is your correct answer. Now interestingly, without even looking at the numbers here, I think the NMR data itself gives you some indication that the aromatic ring system is actually symmetrically substituted, because you have 7.9 which corresponds to 2 hydrogens, and you have 6.6 which corresponds to 2 hydrogen. So you can see in choice 1 is a symmetrically substituted ring, okay, and choice 3 also is a symmetrically substituted ring. On the other hand, choice 2 and choice 4 are not symmetrically substituted. So that itself, the data itself, which indicates some symmetry of substitution in the aromatic ring, rules out choice 2 and choice 4. Right. So now we have left with two choices, choice 5, choice 1 and choice 3 with 5 signals each. So which one is your correct answer here? Right. Now here the key part is the D2 exchangeable hydrogens. If you look at this data, 4 ppm, a broad singlet with 2 hydrogens which are D2 exchangeable. Right. Now if you look at each one of these choices, see NH2 there, so those are D2 exchangeable. You have another NH2, CONH2 here, which is D2 exchangeable. And well, these two we have already ruled them out, but these two NH2s are also D2 exchangeable protons, right? So how do you make out of 1 and 3 which is your correct answer? Right. See, there's something interesting about the way the exchangeable protons are connected. If you have a structure like this, say for example an aniline like that, right? Now these D2 exchangeable protons will generally come at around 3 to 5 ppm, right? Whereas if you put a carbonyl group, okay, right, at C double bond O NH2 in between, if you put a carbonyl group like that, well, that will be more downfield, obviously because of the anisotropic effect of the C double bond O, that will be between 5 to 9 ppm. So if you really think about this data which is given in the problem, which is at 4 ppm, a broad singlet, 2 hydrogens D2 exchangeable, you know very clearly that your structural motif has to be something like this, right, which is 3 to 5 ppm. So that technically rules out choice 3 as well. So even choice 3 is ruled out. So choice 2 obviously is ruled out from the symmetry of this ring substitution. Choice 4 is also ruled out. Well, choice 3 can be ruled out from the data on the exchangeable hydrogens, whereas choice 1 is your correct answer, right? Thank you.